Okay, so I will go on discussing the physics of light. I remind you that during the last 4 lectures, I talked about quantum physics. I talked about the rules of quantum theory, the way you can understand the microscopic world by using the postulates of quantum physics. In the last 2 lectures, I also introduced the angular momentum and the spin, which are very important for the experiments I will be talking about today. And in the last lecture, I talked about entanglement, about the feature, the fact that when 2 quantum systems have interacted, they remain linked to each other by what is called entanglement, kind of correlation, which cannot be understood in classical terms. So today I will start a series of 3 lectures, lecture today and next week and the week after, which will be devoted to the evolution of quantum science in the domain of atomic physics and quantum optics in the 20th century. I will show to you that the fundamental discoveries which have been made at the beginning of last century have been followed by a lot of application, a lot of inventions of devices which play a very important role in our everyday life. And there is a mixture, a kind of symbiosis between fundamental work, fundamental research, and applied research, which is very typical of this kind of physics. For instance, the focus will be on the development of new coherent electromagnetic sources working in the radio frequency domain, but also in the optical domain with a laser, and beyond the optical domain in the UV and X-ray range. And I will give you a few examples of that. And I will discuss the application of these sources in basic science to probe and control atoms and molecules. I will talk about magnetic resonance, double resonance, optical pumping, and describe also high resolution spectroscopy and its application to atomic clocks. And I will also insist upon the fact that in many experiments, quantum interferences play a very important role. So all this physics is exploiting state superposition and quantum interference effects. Just to make a little advertisement on these 2 slides, I summarize very briefly what I will be talking about. Today, I will talk about the birth of modern atomic physics. I will talk about the experiment by Stern and Rabi, the invention of nuclear magnetic resonance, the origins of the atomic clocks and the maser. And I will talk also about the lamp shift and the beginning of quantum electrodynamics. And the lamp shift is a very important experiment, which is of fundamental value because it's the first demonstration of the importance of the vacuum field in physics. Then I will talk about magnetic resonance. I will enter into more details. I will describe how you can quantitatively analyze an experiment in magnetic resonance. I will talk about the Larmor precession, Rabi oscillation, and I will talk about the spectroscopies that you can make in magnetic resonance, Rabi pulses, Rabi and Ramsey spectroscopy. And I will also introduce briefly how you can deal with relaxation effect, how you can deal with the fact that the spin system that you are studying is coupled to an environment which you are not looking at. So the question of entanglement will again come up in this context. We'll also discuss the difference between what happens if atoms interact with a coherent field, a field which has a well-defined phase and amplitude, and what happens when it interacts with classical light, which is incoherent, which has phase fluctuation and amplitude fluctuation. And there is a very important difference between these 2 kinds of behavior. Then next week, I will talk about new methods to manipulate atoms, double resonance and optical pumping. I will introduce also the laser, because the laser has come up in the middle of last century from these experiments in optical pumping and in magnetic resonance. I will talk about the laser, and I will discuss the advantage of the laser over classical sources, taking into account the importance of its intensity, of the directivity of the laser beam, of the monochromaticity and long coherence times. And I will say a few words about extreme light, very intense light sources, and the experiments they allow us to do, which were absolutely impossible to do with classical light. Then I will talk about high resolution spectroscopy. I will explain how you can suppress the Doppler effect, which is the big enemy of spectroscopy. The Doppler effect is broadening the absorption and emission lines of atoms. And there are some nonlinear methods which allow you to get rid of the Doppler effect. Then I will discuss another method which allows you to get rid of the Doppler effect, which consists in trapping atoms, forcing atoms to remain as motionless as possible to do spectroscopy. And I will start by talking about ion trap physics. And in the end of this panorama, I will summarize everything by insisting upon the importance of state superposition and quantum interference effects in these experiments. So let's start with a historical survey of atomic physics in the 20th century. I will start by doing a kind of historical overview, talking about the important experiments which have been performed, let's say, between the 1920s and the 1950s. Then, in the second part of the lecture, I will talk about, more precisely, I will talk about magnetic resonance and give you the mathematical formula and the framework which allow you to compute what happens when you do an experiment on spins or on two-level systems, whether you do it in the microwave or in the optical domain. And in the end, I will discuss the difference, what I already alluded to, the difference between the coherent excitation of atoms, which are driven by monochromatic light, and the broadband excitation realized by classical incoherent radiation. And in this context, I will revisit the notion of the absorption and stimulated emission and spontaneous emission coefficients, which I already introduced when I talked about Einstein analysis of the blackbody radiation problem. So let's start with a very important experiment which was performed in 1922 by Stern and Gerlach. Otto Stern was working in Hamburg, and he developed a method of atomic beam physics. So what he did was to evacuate air from a partition, having a space where you had a very good vacuum. And he had an oven. In the oven, he had atoms. He had a sample of silver. He heated the silver. Silver evaporated. And in vacuum, he had a beam of silver atom propagating horizontally. And he put these atoms inside. He had these atoms traveling along a magnetic field gradient produced by a very powerful electromagnet. What he wanted to study is the magnetism of atoms. He knew that atoms carried magnetic moments, and he assumed that to measure the magnetic moment, he could look at the deflection of the atomic beam. And what he expected is to see on the plate that he put as a detector here, to see a continuous trace, because depending upon the angle that the magnetic moment was making with the direction of the gradient, he expected to have a continued distribution of projection and have a continuous trace. And to his great surprise, what he observed is, in fact, that the atomic beam was just dividing into two parts. One part of the beam was going up, the other part was going down. And what he discovered in this experiment is the spatial quantization, which I discussed last week, the fact that the spin or magnetic moment, atomic magnetic moment, can only take discrete values along a given direction. In this case, what he was observing, in fact, is the spin of the silver electron spin. The outer orbital of silver, there is one electron, and this electron can point up or down, and he saw for the first time this spatial quantization. What I want to remind you is that if the magnetic moment was initially perpendicular to the z direction, we know now that, in fact, this is a linear superposition of up and down. So if the spin starts like that, part of the wave function will go up and part of the wave function will go down. So in this experiment, you have the concept of entanglement. The spin is entangled to the trajectory. If the spin is up, the atom is going up. If the spin is down, the atom is going down. So there is an entanglement between the spin and the orbital variable. Of course, Stern did not know this about entanglement, but what he observed is the trace that I show you now on the right part of the slide. You see here, this is the first observation. He saw that he had the up and down trace. On the edges, the two lines were collapsing together because the magnetic field is much smaller on the edge, and so the separation is weaker and you have maximum separation in the middle. So this signal is very important. In fact, this is a signal which heralded the quantum revolution in technology, because most of the experiments I'll be talking to you about are experiments about spins or two-level systems that you can interpret from this quantization, from this spatial quantization, and a lot of technologies have come from that. The next step was, in fact, due to a postdoc who was working with Otto Stern in Hamburg, an American, Isidor Isaac Rabi, who spent 1 year in Hamburg. And when he came back to the United States at Columbia University, he started a research group to develop the method of atomic and molecular beams that he had learned with Stern. And in fact, he improved Stern's setup in the way I'm describing here. Along the propagation of the atomic beam, you have three zones, A, B, and C. In zone A, there is a gradient of magnetic field which pushes the atom up. In zone B, it's the opposite, it pushes the atom down. And you see that due to these two fields in opposite direction, the trajectory of atoms has a kind of S shape. It's going up and then down. And it is focused on the detector. The detector is a hot wire, a metallic wire. When the atoms or the molecules hit this wire, electrons are ejected and there is an electric current. And by measuring the electric current, he can know what is the flux of particles which reach the wire. So this is a kind of improved Stern setup, but the real innovation is what happens in zone C in the middle. In zone C, he applied a microwave, a resonant radio frequency field. This field had a frequency which was required to flip the spin from down to up. So you see that if, for instance, the field was in the atoms are in the up state, they follow this trajectory, and then they want to do that. But if you flip them to the other state, they will just be deflected in another direction and they will miss the detector. And so if you look at the current of the detector as you scan the frequency of the microwave, or for a fixed microwave, when you scan the magnetic field, you will see a resonance, a curve with a dip. And this is what I show on the slide now. So this is called a resonance. It's an effect which occurs only when the microwave produces photons which have exactly the energy required to flip the spin. And in the following of the lecture, I will give you the formulas which allow you to make quantitative calculations. But here, I just give you a kind of qualitative estimation of what happens. And you see that the position of this resonance depends on the magnetic moment, of course, of the particles that you are looking at. And so you can measure magnetic moments in this way. And Rabi and his students measure the magnetic moment of many nuclei, for example, hydrogen, deuterium, helium, cesium. So these are atoms that he also measured magnetic moments of molecules. So it was a very broad range of experiments, but I want to show you now that these discoveries have really opened the way to magnetic resonance imaging, to atomic clocks, to the GPS and to the laser. In fact, all these inventions have started from research done at Columbia University back in the 1930s. In fact, Rabi was aware of the fact that it was important. He gave a talk in 1939, and there were journalists attending to the talk, and this is the headlines which are published in the New York Post in December 1939. And you see this, it says, "We are all radio stations, Columbia scientists report, all atoms in humans or in steel found to emit and receive long waves." So what I think what Rabi has said is that the atoms or molecules that I have in my beam are the same as the atoms or molecules you have in your body. For example, you have a lot of water and protons. And if you apply a radio frequency field, you will put them in motion and they emit microwaves. And so you have inside your body microwave emitters like a radio station. And these waves could be used one day for something. In fact, of course, this is a premonition of magnetic resonance and magnetic resonance imaging, which is exactly doing that. So he predicted that. He also predicted the atomic clock. And I will just show you how it happened. In fact, the next great advances came in 1945, just after the Second World War. Felix Bloch is the same Bloch as the Bloch of the Bloch sphere, the Bloch equation. He was a great physicist working, who came from Europe because he left Germany and Switzerland before the war because of Nazism, and he worked in the United States. And Ed Purcell was working at Harvard, and they both discovered independently nuclear magnetic resonance. So it's the same idea as Rabi, but instead of working on an atomic beam, they worked on the atoms which you can find in solids or in liquids. And they applied the magnetic resonance technique. So you have a sample here which contains a liquid or a solid system. And then you have a very big, very powerful magnet. And you have radio frequency coils. So you can emit microwaves or radio frequencies which set the spins in motion. And you have a receiving coil, a coil which receives the signals which are emitted by the atoms, and then you can record this on a recorder which displays the response versus frequency. So this is a principle of nuclear magnetic resonance. I just want to stress that this could be developed after the war because great progresses have been made during the war to emit and detect radio waves. In fact, this was a physics which was developed for the radar system. And there was a big radar lab at MIT, and a lot of physicists who were working just after the war on this topic had been working for the war effort on the radar in the United States. And this, of course, nuclear magnetic resonance has become very powerful and very fertile ground of research. Now, 80 years later, you have still a lot of work being done in physics, in chemistry, in biology, using the nuclear magnetic resonance method, because it's a way to probe the nature of the elements that you have inside your body or inside any sample, liquid or solid sample. But it's also a way to investigate the environment, because the lines, the resonance lines, are shifted and broadened by electric and magnetic fields. So it's a way to test what happens at the microscopic level in the environment of molecules and atoms. And it's a technique which is used, as I said, in chemistry, biology, and physics in a lot of domains. And in fact, it has also been used some 30 or 40 years later to develop MRI. So I remind you what magnetic resonance imaging is in medicine. You may have seen these big magnets. These are superconducting solenoid in liquid helium at very low temperature. And when a patient has to be investigated, you have to put it in this big magnet. What happens is that the molecules of water you have in your body carry two hydrogen atoms with their proton, and the proton is a spin, which has two different energy levels depending upon whose separation is proportional to the magnetic field. And so if you apply a microwave with photons having an energy resonant with this separation between the levels, you will put these spins into motion. And this is the basis of NMR applied on water inside the bodies of people who are being investigated. The idea is that if you put an inhomogeneous magnetic field, if the magnetic field varies with position, the frequency which will be required to excite the spins in different places will be different. And so you will have a kind of mapping from position to frequency. And with powerful computers, you can use this information to reconstruct the density of protons inside your body. And this is exactly what an MRI is doing. On the next slide, I just give you a brief idea of how it works. Assume that you have three positions here. and the magnetic field increases from left to right. So here you need small frequencies, radio frequencies to induce transition, here larger frequency, and here even bigger frequencies. And the spins which are excited at different points radiate microwave at different frequencies. Then you have a pickup coil, big antenna, which collects this microwave. In fact, this oscillating field are inducing currents in the loop, and you measure the frequency of this current, and you know from which place the signal came, and you send this to a computer, which reconstructs the image. And I just show you on the next slide a kind of picture you get. This is a MRI of the brain, and you have a version of MRI which is now very much developed, which is called functional MRI, which means that you are investigating, looking at the magnetic resonance signals while the patient is doing something. For instance, you ask him to move his arm, or you ask him to think about something. This activates some parts of the brain. And when the brain is activated, the flux of blood coming to this part increases. You know that the blood is containing hemoglobin molecules, which contain iron, which is a magnetic material. So when this magnetism increases at some point in the brain, the signal changes because the signals are sensitive to the magnetic field. And you see literally some parts of the brain which are lightened up when the brain is doing something. And this is very useful, not only for medicine, but also for research, brain research, and to understand how the brain is working. There are even some people who are investigating the emergence of consciousness when you ask the patient inside the machine to think about something, do some task. And this is, of course, something which was completely unexpected when Bloch and Purcell invented nuclear magnetic resonance in the 1940s, because it was impossible to do at that time. There were no computers, there were no high magnetic fields produced by superconducting coils. And this is really a conjunction of several research areas, fundamental and applied, which led to this very important application of magnetic resonance. Another application is the atomic clock, and I just show you here very briefly the principle. It's again a Rabi machine. It's a molecular atomic beam machine, but now the improvement is that instead of having one zone in which you apply the microwave is split into two parts. So the atoms are subjected to a first pulse of microwave when they cross the first zone, and a second pulse after that. This technique was invented by Ramsey, who was a student of Rabi. And when you do this double zone excitation, the resonance that you observe has now fringes into it. And I will show you, when I will discuss that later, I will show you that these fringes are related to quantum interference. So the signals that you observe, instead of having one line, you have fringes like that. And if you sit on the top of the central fringe, you in fact define the frequency with a very high precision. And so what the system is doing is to detect the resonance and then to send a signal which locks the source of microwave to be exactly at the center of the central fringe. And in this way, you get a very stable microwave. It is done with cesium atoms. In the ground state of cesium, you have a transition around 9.2 gigahertz. So it's the microwave domain. And this very stable source is a clock. It gives periodic signals at 9.2 gigahertz with a precision and uncertainty of only 1 part in 10 to the 14, which is a huge improvement with respect to previous clocks. And these are the clocks which are being used in the GPS system. They are sent in satellites, and they send signals to us. And with that, and I also already talked about that, you can localize yourself anywhere on the Earth with a precision of about 1 meter. So, and you need this kind of precision. And of course, this is not only quantum physics, but it's also exploits relativity, because you have to take into account spatial and general relativity to make corrections. So this is another application. Another application which again came from the same lab is the invention of the maser, which is the ancestor of the laser. You see here a picture with You see Towns and Gordon with their first maser. It's an atomic beam machine. In fact, it's a molecular beam. The first masing medium was ammonia molecules. And there is a transition in the ammonia molecule which occur in the microwave domain. And what they were able to do is to inject inside their cavity molecules in the upper state of the transition. So stimulated emission was the important effect. And the microwave were amplified inside this cavity. And this was the first system of this kind. And they coined the name maser for an acronym for microwave amplifier by stimulated emission of radiation. This is Einstein's idea, but it took something like 30 or 40 years between the 1916 paper by Einstein and this first realization of the maser. And immediately when the maser was invented, Towns and others have started to try to extrapolate, to generalize this in the optical domain. And of course, it happened a few years later, and they just replaced the M of maser by L. And it was light amplification by stimulated emission of radiation and the laser. So the maser is just the ancestor of the laser. And when it was invented, nobody knew what would be the use. A lot of people asked themselves the question, what will be the use of this new device? And of course, we don't have to ask this question now. This will be the topic of several lectures. Now, another big discovery which came from the same group, Columbia lab. One of the students who had been working with Rabi was Willis Lamb. And Willis Lamb made a fundamental experiment that I want to talk a little bit to you about, which is a measurement of what is called the Lamb shift. The idea is that it comes from the Heisenberg uncertainty relations. As I told you a couple of weeks ago, due to these uncertainty relations, an oscillator, a mechanical oscillator, cannot be at rest. It has small fluctuations of its position around equilibrium and of its velocity, momentum, because there is an uncertainty between position and momentum. This happens for all oscillators. There is a residual 0-point fluctuation, which corresponds to half a quantum, h bar omega over 2. And this happens also for the electromagnetic field, because this field has the same structure in the equation. You can say that the electric and magnetic components are like the kinetic and potential energy of a mechanical oscillator. So you have, for the electromagnetic field in any volume, tiny fluctuations which are distributed along frequencies. And these fluctuations have an effect on atoms, because these are electric and magnetic fields which act on the electron. And this will perturb slightly the energy levels. And this is something which was not predicted in the Dirac equation. Now, this fluctuation of the electromagnetic field are very important in electromagnetism, but they have been generalized when the field theory have been developed in the 1950s, 60s, and so on. One has understood that all the particles are in fact quanta of their own field. And so you have fluctuations of all the field, not only the electromagnetic field. And this fluctuation explains the fact that the vacuum, what we consider to be the vacuum, is in fact full of particles, not only virtual photons, but also particles which are created and disappear very quickly. And this is very important, for instance, in cosmology. To understand the nature of the vacuum is something which has to do with cosmological theories and understanding of how the universe evolved. So I don't want to enter into these details, but I want to say that this experiment, which I will be talking to you now about, has been very important in this respect. What the experiment I will describe to you is, again, a radio frequency experiment. And again, it benefited from the progress made during the war. In fact, Lamb had been working at MIT in the radar lab, and he used the techniques that he has been learning to do these fundamental physics experiments that I will be describing to you now. So first of all, what is the Lamb shift? I remind you, 2 weeks ago, I said a few words about Dirac equation, and I told you that this relativistic equation made it possible to compute with high precision the spectrum of the simplest atom, which is hydrogen. So in hydrogen, you have a ground state, which is an S state. I remind you that S state means that the angular momentum of the electron is 0. So the wave function, the ground state, has a spherical symmetry. It's the same in all directions. You see it here. In the excited state, you have L equals 0, which is again an S state, and you have L equals 1, which is a P state. The orbitals are much bigger because you know that the size of the atom increases as n squared. So the size of the orbital is 4 times bigger in n equal 2 than in n equal 1. And you see that there is a difference of symmetry. The S state has a high probability for the electron to be at the nucleus. In the P state, you have the Y1 spherical harmonic is 0, gives 0 value at the nucleus, and you have a positive and negative lobe. And I told you there are 3 states which are oriented in different directions because M can take the value +1, 0, and -1. So this is Dirac's equation. And an important feature is that Dirac equation tells you that the 2s and 2p states are exactly degenerate. They have the same energy because of the symmetry of the problem. Now, what will happen when you take into account the fluctuation of the vacuum, the vacuum fluctuations? What happens is that, in fact, the S states are sensitive to the vacuum much more than the P states. And so the S states are shifted up. And you see that what happens is that the 2s state now has an energy a little bit larger than the 2p1. The 1s state has an energy much larger. In fact, the lamp sheet in the ground state is 8 times what it is in the 2s state. So how do you measure this lamp sheet? Of course, the simplest idea would be to measure just the separation between the ground state and the excited state. This is done now with lasers, but at that time, this was impossible. There was no way to do precise spectroscopy in the optical domain. On the other hand, to measure in this state is much easier because you take advantage of the fact that the 2p state does not move. So in fact, the 2p state is a kind of reference which will allow you to measure by difference the motion of the 2s state. It's exactly what LAMP has done. So, but before describing LAMP experiment, I will try to give you a little flavor of what happens, in fact. What happens, you see the hydrogen atom, this is the nucleus, and here you have the electron. And what happens is that the vacuum fluctuations are shaking the electron. This rapid fluctuation of the field makes the electron move around its equilibrium position. And so you see that the electron is now exploring the potential of the nucleus, not at a given point, but in a small volume around this point. And what I have done here is to develop what happens. You see, if you want to compute the potential energy, what you have to do is to take U at point R plus epsilon, epsilon being the excursion of these fluctuations, and you have to average over position, multiplying by function f of epsilon, which is a kind of shape function, which tells you how big is the excursion around the value epsilon equals 0. And since epsilon is small, you can develop, and you have a first order term, and then you have corrections to first order. The correction, in fact, to first order, the correction is proportional to the gradient of u times epsilon, but epsilon can be positive or negative, and so this term has a 0 average. The first term which matters is the second order term, and the second order term is multiplied by the second derivative of u, which is d over dx squared plus d over dy squared plus d over dz squared of u, which is just the Laplacian of u. So you see that the effect is proportional to the Laplacian of u. And the Laplacian of u for a point charge, we know what it is. In fact, the Laplacian is the divergence of the gradient. The gradient of u is the electric field, by definition, and the divergence of the electric field is just the charge. This is the Coulomb equation. So what you have indeed is that this perturbation is proportional to the charge distribution, and we know that the charge is centered at the nucleus. So the perturbation is proportional to delta R, where delta is just a Dirac function, the delta function at R equals 0. And you understand now why S states are the only one which are affected, because S states have a probability for the electron to be at the nucleus, while P states have a 0 probability. So in fact, because of this Laplacian, only the S states are being affected. So then I continue to try to give you an order of magnitude. How do you compute now the excursion, the size of this fast motion of the electron around its equilibrium position? You make a very simple model. You assume that the electron is free. Why? Because I will look at the contribution at very high frequencies, at frequencies omega, which are much higher than the optical frequencies that the hydrogen atom can emit or absorb. So it's like if the electron were free. And it's very simple to compute how a free electron reacts when you push it up and down. You just write that its acceleration is equal to the force which is applied, which is proportional to the electric field. And once you have the acceleration, if you integrate twice, you find the excursion, and you find that the excursion is given by E squared over omega squared. It's just the response of a free electron to a very fast oscillation. So you get this, and you get this expression for each mode of the vacuum field. And of course, you have to sum over the modes. So when you sum over the mode, you get this kind of expression for E squared. So this is the effect of one mode. This is the number of modes per frequency interval. This is the same. This is the mode density, which I have used when I talked to you about the black body radiation, the number of modes per unit frequency interval. And I have to multiply by this quantity, which is E squared. E squared is just, what is E squared? Just the fluctuation of the vacuum, h bar omega over 2, divided by the volume over epsilon naught, and you take this. This is the value of E squared. So when you put all this, you find this expression, and you have to integrate something which is d omega over omega. D omega over omega will give you logarithm of omega when you make the integration, and you have to find what is the upper bound and the lower bound. Of course, you cannot integrate to infinity, because if you go to very, very high frequencies, what will happen is that you enter into relativistic domain. And so at that point, the mass of the electron will increase. And so the excursion of this vibration will become smaller and smaller. So you have a natural cutoff when omega is of the order of mc squared. So this is the upper limit. And the lower limit is omega of the order of the atomic transitions, because here I made the approximations that I can neglect the attraction to the core. And the difference between the high frequency and the low frequency is alpha squared, where alpha is the fine structure constant. So in fact, you have a log of alpha, which is something, you know that alpha is 1 over 137. This is the fine structure constant, and you have this logarithm which comes into the expression. And when you put everything into place, and I just give you an estimate, you find that the lamp shift, the displacement of the S equal 2 state is given by this expression. And of course, you have to multiply by the probability to find the atom at the nucleus, psi squared. And psi squared is 1 over psi squared, the value of the probability to find the atom at the nucleus is 1 over a naught squared, something proportional of 1 over a naught cube, where a naught is a Bohr radius, because the probability, the extension of the wave function is of the order of a naught cubed for the volume. So you have a 1 over a naught cubed factor here. I made a mistake in my lecture notes. It's 4th power, not 6th power. And it's log 1 over alpha, not log alpha. And eventually you find this result. You find that the lamp shift is proportional to alpha to the 5th power logarithm of 1 over alpha. And this is, of course, just an estimate, because I made a back of the envelope estimate of the upper and lower bounds of my integral. But when you do that, and when you put all the figures here, what you find is something which is of the order of magnitude of the lamp shift. You find about half the lamp shift, which I will show you in a moment. I remind you that the fine structure constant is given by this expression. It's a dimensionless quantity. And I apologize for the mistakes, but I found that I am not the only one to make mistakes. And since we are talking here about the Fermi lectures, I show you here a very famous picture of Fermi talking about the hydrogen atom. And look at how he wrote the fine structure constant. I will just, you see, not only he confused H and E. Instead of writing E square over H bar C, he wrote H square over EC. So, and this is a famous picture because its picture have been reproduced on a stamp celebrating, I think, the 100th anniversary of Fermi or something like that. So you see, you can make mistakes, and this is I take solace in this kind of reflection because there is no doubt that Fermi knew what the fine structure constant was. So let's go now at the description of the experiment. So you see what happens. The 2s state is a little bit above. In fact, the value of the lamp shift is about 1 gigahertz. The 2s state cannot decay to the ground state by emitting a photon because it's a forbidden transition. There is no electric dipole coupling between these two states. So this means that the 2s state has a very long lifetime. It can only radiate 2 photons, not 1, and this is very highly improbable. On the other hand, the 2p state has a very short lifetime. As soon as you go in the 2p state, it decays to the ground state in about 1 nanosecond. And I will talk about that a little bit later. So what Lamb exploited this difference, and he made the experiment which I show you here, the principle of here. So you have a hydrogen, you let hydrogen escape from this bottle in vacuum, and on here you bombard hydrogen molecules with an electron beam. So this electron beam has 2 effects. First of all, he breaks the molecule into atomic hydrogen, and second, he has a probability of exciting this hydrogen from the ground to the metastable 2s state. So you get atoms of hydrogen in the 2s state, which survive about 1/10 of a second, which is very long compared to the time it takes to cross the apparatus. And then here you apply microwaves around this frequency. And you see when you hit the right frequency, the atoms go from 2s to 2p, and then they disappear immediately to the ground state. And so on this cathode, the metastable atoms don't arrive on the cathode anymore when you apply the microwave. And what happens if the metastable atoms arrive here, they extract, because they have a lot of energy, on collision, they come to the ground state and they eject electrons that you can detect with this galvanometer. So you see that you will detect electrons as long as the microwave has not taken out the atom from the 2s state into the 2p state. And so it's again something like the Rabi resonance I showed you before. You have a decrease of the signal when you hit the resonance. And it's exactly what Lamb did. And he measured the Lamb shift in this way. And you have, this is the paper that was published in 1947. A few months later, there was another experiment which demonstrated again the existence of these quantum fluctuations. This time it was not the measurement of the Lamb shift, it was a measurement of the magnetic moment of the electron. And I just remind you that classically, a magnetic moment is proportional to the angular momentum with a ratio Q over 2m. What Dirac has shown in his equation is that in the case of the electron spin, the ratio is not Q over 2m, it's just twice that, it's Q over m. So Dirac equation predicts that the electron should have a gyromagnetic ratio twice that of the orbital one. But this is not taking into account the vacuum fluctuations. And in fact, Kush, who was again a collaborator of Rabi at Columbia, made a spectroscopic measurement that I don't want to describe you here, which compared the Zeeman effect, the magnetic field effect on P1/2 and P3/2 states. I remind you that P1/2 is a state which has a total angular momentum of 1/2, and P3/2 has a total angular momentum of 3/2. They're obtained by combining the spin 1, the angular momentum 1 of the orbital momentum with 1/2 or plus 1/2 or minus 1/2 for the spin. So he looked at the Zeeman effect for these two states, and he found a ratio which is consistent with the fact that G is slightly different from 2. And in fact, he found a value, G is equal to 2 times 1 plus a small correction A. And this correction was found by Schwinger, who was a theoretician, again, a student of Rabi, who said that A should be equal to alpha over 2 pi, which is just 1 part in 1,000. So it was again a demonstration of the fact that vacuum fluctuations played an important role. But you see, Kush made a measurement of about 1 part in 1,000. Since then, huge progress had been made. I don't have time to describe the experiments, but they are performed in a trap in which you can trap a single electron and observe this electron for a very long time. And you see here now how we know with which precision we know the G-2. You have 10 significant digits. And the theory, which computes the higher and higher order effects of vacuum fluctuations, coincide with the experiment up to the 10th digit. So this is the most spectacular agreement between theory and experiment in physics. The fact that you can predict with 10 significant digits the value of a fundamental quantity like the magnetic moment of the electron. In fact, Feynman once said that if the distance between, for instance, between Rome and New York could be predicted by quantum electrodynamics, it will be known with the precision of the width of a hair over the 6,000 or 7,000 kilometers. That's what 1 part in 10 to the 10 means. So this tells you the fantastic precision of this kind of physics, which started in the 1940s, 1950s. Similar experiments have been done with a single positron, and experiments measuring the anomalous magnetic moment of the muon, which is a heavy electron, are now being performed, and they seem to indicate that you have some contribution to these vacuum fluctuations, which cannot be explained by the standard model that we have now. So there is maybe some new physics which will come from this kind of experiment. So now a few remarks about magnetic resonance. I want to give you the formulas which allow us to compute with precision all these experiments. I will start by talking about the Larmor precession of a spin in a magnetic field. The Larmor precession is the fact that when you put a spin in a field, the spin precesses around the field at a frequency proportional to the amplitude of the magnetic field. And this is something which can be understood easily. Here, I remind you this formula, which comes from Ampere, the fact that a current loop gives rise to a magnetic moment, which is equal to the current times the surface of the loop. And if you put the figures here, you find, again, that the ratio between the angular momentum and the magnetic moment is Q over 2m. So classically, you find this Q over 2m value. And I remind you here that according to Dirac, you have twice this value in the case of the spin, which is not a classical variable. So what happens classically if you put a spin in a magnetic field? You just write Newton's equation. How do you express Newton's equation for the angular momentum? The derivative of the angular momentum is equal to the torque applied to the system, and the torque is just the cross product of the magnetic moment by the magnetic field. So this torque gives you ds over dt. And if you express this, and you can express the torque, you know how you compute the torque, and you write for x, y, and z, you find this very simple equation. And you find that the real variable is Sx plus Isy, and Sx plus Isy is evolving at the frequency omega naught, at the Larmor frequency omega naught. And when you express this on the 3 coordinates x, y, and z, you find the precession you find that S of t has a component proportional to cosine theta on the z-axis, which is fixed, it does not depend on time. And the components across in the x or y plane are just cosine omega naught t and sine omega naught t. This is just a circular motion. So you see, when you solve this equation, you find that the projection of the spin along the magnetic field is fixed, and the projection of the spin in the plane perpendicular to the magnetic field is rotating. This is a kind of conical rotation, which is typical of the Larmor precession. And the orders of magnitude, when you compute Q over 2m and you put all the figures, you find that the Larmor frequency is of the order of 2.7 10 to the 4 hertz per Tesla for the electron. And it is, so it's about 2 megahertz per Gauss, if you want to take units which are more practical. A Gauss is about the magnetic ambient magnetic field of the Earth. So you see an electron spin rotates in the range of megahertz in the field of the Earth. And if you look now at a nuclear magnetism, because m is much bigger, the frequency is much smaller because it's Q over m. And so you have about 3 or 4 orders of magnitude smaller for nuclear spins, which is of the order of kilohertz per Gauss in the Earth's magnetic field. So these are the frequencies. And you see that if you want to have high radio frequencies, the one we need for MRI, you have to put huge magnetic fields. And we'll come back to this in a moment. And what else here? I want to make an analogy with this kind of rotation, which keeps the angle between the axis of rotation and the direction, like the z-axis fixed, reminds what happens when you have a top. You know, when you have a top which is rotating very fast and you put it on the ground, what you see is that it does not fall. It goes around, it rotates very fast, and it has at the same time a nutation motion around the vertical. This is exactly for the same reason, because the torque which is applied to this rotating top, this torque has, in fact, it's made of 2 forces. You have the gravitation, which wants to pull it down, and you have the reaction of the ground, and it makes a couple, a torque, and this torque makes the thing rotate but does not fall. And so, in fact, the Larmor precession is like the rotation of mechanical top, and you understand why it's not going to align itself on the magnetic field. It keeps an angle fixed between the magnetic field and the axis of rotation. Now you can understand that also in quantum mechanics, and I will do it very briefly because we already studied this point. If you look at the quantum state representing a spin, we know that you can represent it as a vector whose tip is on the Bloch sphere. Any point of the Bloch sphere is a quantum state for a spin 1/2. If you put the system in the magnetic field, you see this point will go around the z direction. You will have a rotation of the tip, and this rotation, you can understand it from Schrödinger's equation. So what I did on this slide is just to write the Hamiltonian, which is minus mb. M is the magnetic moment, b is the magnetic field. So minus mb, b is a line along the z-axis, is proportional to sigma z. So the Hamiltonian is proportional to sigma z, which means that the plus and minus states are evolving like E minus I omega naught t or E plus I omega naught t, depending upon whether there's a plus or minus eigenstate of sigma z. And if you start on the side with a spin pointing on the side, it's a superposition of the two. And so you will have the wave function, which I show you here. You will have a superposition of a motion with the phase E minus I omega naught t over 2 and E plus I omega naught t over 2. And when you put that in the expression of the wave function, you find this, which is just the tip of a vector which rotates, keeping theta constant and phi evolving at the frequency omega naught. So you find, by quantum mechanics, you find exactly the same Larmor precession that you have in classical physics. The Bloch vector, which represents the spin of the Bloch sphere, rotates around the z-axis with a Larmor angular frequency omega naught. and the angle theta between the magnetic field and the spin direction remains constant. So we find, again, the same result. Now, what is magnetic resonance? For the time being, I just described what is the energy of a spin up and a spin down. Since the energy are different, it means that if you take a spin on the side, the amplitudes will evolve differently and it will be a rotation. But how do you flip the spin from the up to the down position? What you have to do is to apply a radio frequency. And the simplest model you can take is to assume that the radio frequency field is rotating in the plane perpendicular to the z-axis. So you have a circularly polarized RF field, which is rotating like that. And you want to study how the spin will evolve. And the trick is to go in the rotating frame. That is to sit with the rotating magnetic field and to look at how you describe the physics in this rotating frame. So what happens? Suppose that the spin is processing at the Larmor frequency omega naught. If you rotate at frequency omega, you will see the spin processing at the frequency omega naught minus omega. If you process exactly at the same frequency as the spin, it will be fixed in your frame. So in fact, you see that in the rotating frame, the spin, it is as if you had reduced the magnetic field, transforming omega naught into omega naught minus omega. And what about the field, the RF field? If you are at the frequency omega, it will be fixed because you will rotate with it. So you see that in the rotating frame, the problem becomes time independent. In the rotating frame, it is as if you had a component omega naught minus omega along the z-axis and a component omega 1 along the x-axis, all being frozen independent of time. And this is the physics in the rotating frame. And now we know exactly what is the physics in the rotating frame. You see, in the rotating frame, the z component has become delta over gamma. This is a geometrical issue. Delta is a mismatch between omega and omega naught. So in the rotating frame, everything happens as if the field had been reduced from omega to omega minus omega, from omega naught to omega naught minus omega. And you have a transverse field, which is given by delta over gamma. So you have now this field. And what you have to do is to understand how the spin rotates along this direction. You see now the direction of rotation is the direction u, which has a component delta over gamma along OZ, and a component minus omega 1 over gamma along the x-axis. What is the magnitude of BU? It's just a Pythagorean theorem. It's just the square root of delta squared plus omega 1 squared. So this field in the rotating frame is given by this expression. And now what you have to do is to compute the rotation along the u direction at this frequency. And we know how to do that. You know that if you have a rotation around sigma u, the rotation is E minus I sigma u over 2 times the angle. So it is what I have expressed here. What is sigma u? Sigma u is a Pauli matrix which is sigma, which has a component sigma z equal to delta over omega r, and the component sigma x equal to minus omega 1 over omega r. So this is normalized. This is sigma u, the direction around which the spin is precessing. You have to take the exponential of this expression. And I remind you that when you do that, you have the identity operator times cosine omega r squared t over 2. And then you have minus I sigma u times sine omega r t over 2. And when I express this, I get this 2 by 2 matrix, which is just a rotation matrix, which depends upon time. And the quantity which interests me is the probability to flip the spin from plus to minus, which is given by this off diagonal element squared. So the probability to flip the spin is just given by what I will show you now at the end of this slide. The probability to go from plus to minus is given by this expression. And you see what happens if you are exactly at resonance. This is just 1. Delta is equal to 0, this is 1. And you find sine square of omega 1 t over 2. So what you find is that the spin is going up, down, is rotating like that. So you flip the spin periodically at resonance. And of course, if you go out of resonance, the amplitude of this rotation becomes smaller because you start to rotate on a cone, which has a smaller, makes a smaller and smaller angle with the z-axis. So this is just a problem of rotation, geometrical rotation. And this is called the Rabi formula, because this is an essential formula to compute how a spin, which is prepared in one state, evolves to the other state under the effect of an RF field. So once you have done that, I show you just on the next slide, I will show you how you use that to do spectroscopy. So, but I will stop at this point for 10 minutes.